There are no tiny solid particles, only excitations of something deeper that fills all space. Think about a calm lake, flat, quiet, still. Now drop a stone. Ripples spread outward, circles moving across the surface. But what actually moved? Not the water across the lake, just the pattern, the shape. Now imagine a stretched bedsheet, pulled tight at the corners. You tap the middle. A pulse travels outward. Again, the fabric stays. Only the disturbance moves. So here's the idea. A pattern can move, without matter traveling with it. Hold on to that, because physics will now stretch it to the entire universe. For centuries, we pictured matter as particles, tiny objects with definite positions and clear paths like miniature billiard balls. An electron was thought of as a small charged sphere moving around a nucleus. This model worked for basic predictions, electric currents, chemical bonds, simple interactions. So the intuition grew stronger. Zoom in further, you just find smaller pieces. Same logic, smaller scale. But experiments began to disagree. Electrons formed interference patterns, like waves overlapping. Yet detectors recorded them as localized impacts, single points. So we had a conflict. Particle behavior and wave behavior in the same entity. This was not a small problem. It was a crack in the foundation. Then came a deeper discovery. Particles can be created and destroyed, not broken apart, but completely gone. In high-energy collisions, new particles appear, different types, as long as energy is conserved. This suggested something radical. Particles are not permanent building blocks. They are temporary events. Even more surprising, the vacuum is not empty. Experiments detect fluctuations, tiny, unavoidable variations. This is called vacuum fluctuation, meaning even nothing has activity. So physicists asked, what is really fundamental? And the answer shifted from particles to fields. Now we introduce a key term, a field. A field is a quantity defined at every point in space. For example, temperature in a room. Every location has a value, even if nothing is moving. Now imagine a quantum field. This is a field that follows quantum rules, meaning its energy comes in discrete amounts. These discrete amounts are called quanta, singular, quantum, plural, quanta. Now here's the crucial idea. A particle is one quantum of its field. An electron is one quantum of the electron field. A photon is one quantum of the electromagnetic field. So what we call a particle is actually a localized excitation. Let's define that. Excitation means a disturbance above the lowest energy state, like a ripple above calm water. The calm state is called the ground state, or vacuum state. When energy is added, the field gets excited. That excitation behaves like a particle. Now a simple equation appears here. E equals hf energy equals Planck's constant times frequency. E is energy. F is frequency, how fast the field oscillates. H is Planck's constant, a very small number that sets the quantum scale. This equation tells us energy is linked to vibration rate. Higher frequency means higher energy excitation. So particles are not objects. They are quantized vibrations. Now another term, operator. In quantum field theory, we use operators to create or destroy particles. A creation operator adds a quantum. The annihilation operator removes one. This matches experiments. Particles appear and disappear because excitations can begin and end. Now think again of a guitar string. The string exists. That is the field. A note is played. That is an excitation. Different notes are different frequencies, same string. different vibrations, same field, different particles. Now we go further. The universe has many fields: electron field, quark fields, gluon field, photon field, Higgs field. Each field has its own properties. Some carry charge, some carry spin. Let's define spin. Spin is an intrinsic angular momentum, not literal spinning, but a built-in quantum property. It determines how particles behave. Now, interactions happen when fields couple. Coupling means fields influence each other, exchange energy. This exchange appears as forces. For example, the electromagnetic force comes from the photon field. Photons are exchanged between charged particles, but underneath, it is field interaction. Now the Higgs field. This one is special. Its ground state is not zero. It has a constant value everywhere. This is called a non-zero vacuum expectation value, meaning, even in empty space, the field has strength. When particles interact with it, they gain mass. Mass is not stored inside them. It emerges from interaction, like moving through a thick fluid. More interaction, more resistance, more mass. Now another key idea: superposition. A field can exist in multiple states at once until measured. This allows multiple excitations to overlap. That's why interference happens, even for single particles. This theory is not abstract. It is tested precisely. In particle accelerators, we inject energy into fields. New excitations appear. New particles, exactly as predicted. The Higgs boson was discovered this way. A quantum of the Higgs field. Quantum electrodynamics describes the electromagnetic field. Its predictions match experiments to extreme precision, better than 1 part in a billion. Modern electronics depend on electron field behavior. Lasers use controlled photon excitations. Medical imaging relies on field interactions. So this framework is not optional. It is the foundation of modern physics and technology. And now, the deeper question. What is a field, really? Is it a physical substance or a mathematical tool that organizes observations? We quantize fields, we calculate interactions, we predict outcomes, and everything works. But the nature of the field itself remains unclear. So here's the unsettling thought. Reality may not be made of things. It may be made of fields and their excitations, not objects, but processes, not solid pieces, but structured vibrations. You are not built from particles. You are built from excitations that remain stable for a while. A pattern holding itself together. And when the excitation fades, the pattern dissolves back into the field.